Hello, I am Dimitrios, and I'm going to talk about how to document a Socket.io API. This is a talk that is going to be primarily focused on Socket.io, but I hope it can provide a good example on how to document any event-driven protocol using the AsyncAPI specification. So this is going to be one of the long sessions of this conference, so I think it would be wise to briefly outline some agenda first. I'm going to start with quickly introducing myself and then telling a story from real life on how I discovered AsyncAPI and how I got motivated to combine it with Socket.io. Then I'm going to talk about what Socket.io actually is and how we can model this protocol using the AsyncAPI specification. Towards the latter stages of the talk, we're going to get a bit more practical and try to put together an AsyncAPI file from scratch, given an existing Socket.io API. Finally, we're going to talk about Asynction, a framework combining both Socket.io and AsyncAPI, and hopefully we're going to get some time for Q&A towards the end of the session. I'm now going to share a link to the slides in the chat so that you can navigate through the content at your own convenience. So a few words about me. I live in London, and as you can see here, I chose a photo of London that is pretty characteristic of the London weather. I work at Babylon. Babylon is one of the world leaders in digital healthcare. Our mission is to deliver an affordable and accessible healthcare service to the hands of every human on earth. I am a senior software engineer in the AI chatbot team of Babylon, and throughout my career I've been building distributed systems and cloud-native workloads, mainly in Python and in Node.js. I do have a passion for open source and big data applications. If you're interested in what I'm working on my free time, you can check my GitHub profile and my Twitter account using the Dedoussis handler. I've also recently started blogging in my personal website, and this blog includes articles about this exact topic of AsyncAPI and Socket.io, so if you're interested about them, you can certainly check these out. I'm also the author and the maintainer of Asynction, which is a Socket.io Python framework driven by the AsyncAPI specification. We're going to talk about Asynction in detail towards the end of the talk, so for now you can just stargaze it on GitHub. So how it all started. So my adventures with AsyncAPI date back to the early 2021, where in the chatbot team of Babylon we wanted to extend our chat platform with human-in-the-loop capabilities. So long meetings would soon follow about the design, so whether we should pick a framework X or framework Y, or whether we should go serverless or not. Eventually, the stack of the team, which is Python, Flask, and Kubernetes, pointed us in the direction of Flask Socket.io, making Socket.io the protocol of choice. So this felt a rather unorthodox design process. One could describe it as a stack-driven design process. So the stack and the expertise of the backend team dictated the choice of protocol. I think it would be better if the business requirements or also the requirements of the front-end team contributed equally towards the protocol decision. Thankfully, Socket.io is a very carefully designed and very well maintained protocol, and it ended up fitting our business requirements and front-end requirements and not just our backend team requirements. So essentially we got away with it. So as we moved onwards towards the development phase of this project, I started looking into how we can document our application before actually developing it. So the purpose of this thought was that we could share a contract with the front-end team, and they can start developing their stuff independently to us. So I started looking online on how one could document a Socket.io API, and to my disappointment, I couldn't find any resource on the topic. I tried to zoom out a bit and started searching about how one could document a WebSocket API. Still didn't find many resources. I found a few, but no standardized or widely adopted solution. So it was at this point when I realized that documenting event-driven APIs is treated as a niche area of the industry, which is kind of absurd, because the actual event-driven architectures themselves are pretty popular, especially throughout the last decade. So this left me rather disappointed, especially because I come from a REST and GraphQL world. So for example, in the REST API world, we have the Open API initiative as the de facto standard, and also in the GraphQL or gRPC protocols, everything is strictly typed and contract-driven. So it feels that these kind of APIs have managed to solve this problem for quite some time now, and that the event-driven APIs have lagged a bit behind. So moving onward with my long Google search, I finally came across AsyncAPI. And I was delighted to realize that there is a community out there that tries to solve this exact problem of documenting event-driven APIs. And I was even more delighted to realize that this is a very active and passionate community. So I skimmed through the AsyncAPI specification, and I figured out that this is a tool that I could use for my own problem to document the Socket.io API. So I started looking into how one can document a Socket.io API using the AsyncAPI specification. The only single resource I managed to find online was this Stack Overflow question, which is a very old one and also an archived one. So in the title it says recommendation on how to document WebSocket APIs, but the actual content of the question is about Socket.io APIs. So this question has had only a single answer, suggesting the use of AsyncAPI version 1 and also suggesting it to use in a not very correct manner. So at that point, I realized that no one has really attempted to document a Socket.io API with AsyncAPI. So I decided to take on this challenge and, if successful, write a blog post about it or give a talk about it. So here we are. So before trying to model Socket.io using the AsyncAPI specification, I would first like to establish some basic and common understanding of what Socket.io is. Many would argue that Socket.io is a JavaScript library for real-time web applications, and I wouldn't blame them because this is what the Wikipedia article actually states. However, I do regard this as an outdated definition. I see Socket.io as a protocol of its own, with the JavaScript library just being the reference implementation. It is a protocol enabling event-driven communication. It is a protocol enabling low latency duplex communication. And it is a protocol supported by the underlying mechanisms of WebSockets and HTTP long polling. To reinforce the fact that Socket.io is a protocol, there is an official protocol specification sitting under this repository in GitHub. And also this protocol is implemented in various other languages other than JavaScript. For example, Java, Python, C++, and Rust, and many others. So one would ask, why use Socket.io instead of vanilla WebSockets? And there are plenty of reasons for that. Socket.io is more reliable than WebSockets, and the reason for that is that whenever WebSocket connectivity cannot be achieved because of an old browser version, because there is a reverse proxy or a firewall between the client and the server, then Socket.io falls back to HTTP long polling. Also, there are other features such as automatic reconnection of the client, packet buffering, acknowledgements, message broadcasting, and multiplexing, which we are going to touch upon in a bit. So the caveat is that a Socket.io user, client or server, should never interact with the protocol directly, and they should never interact with they should never care whether it is WebSockets or HTTP polling under the hood. The user of Socket.io should only interact with the Socket class API of the respective implementation library. This Socket class API implements the following symmetrical interface that you see here, and I describe it as symmetrical because it is the same API is implemented by both the server Socket class and the client Socket class. So in the Socket.io protocol, there is not really a server and a client, there is just a sender and a receiver. And the sender can send an event to the receiver using the emit function, and the receiver can receive that event using the handler that is registered using the on function. So again, the on function of the Socket class API registers a new handler for a given event. It implements a subscribing operation, and the callback could potentially return a value that will be sent to the sender party as an acknowledgement, implementing this acknowledgement feature that we already mentioned. The emit function of the Socket class API emits an event to the receiver party, implements a publishing operation, and if an acknowledgement is returned by the receiver, then the acknowledgement callback that you see here as the third argument of the function is invoked with that data. A more advanced concept of Socket.io is the namespace, which essentially it enables multiplexing capabilities. A namespace has its own event handlers and potentially its own dedicated connection. By default, Socket.io uses this single character / namespace, but it is possible for a Socket.io server to support, to set up multiple namespaces, and also to our Socket.io client to connect to multiple namespaces simultaneously. So at this point, where we have only covered the very basics of Socket.io, one would ask, why would we want to document such an API? And I think the answer to that is pretty clear even by now. So here we have a very simple Socket.io server, which in the connection handler we can see that the server emits a few events and also listens to some other events. So on line 4 and line 5 we have the server emitting the hello event, and on line 5 we have the server emitting the greetings event, which is also accompanied by some arguments. The first argument here is just a string, and the second argument is an object, which could be a structured object or it could be like a free dictionary. And then on line 7 and line 11 respectively, we have the server listening to the message event, which expects some data as well, and the server listening on the salutation events, which expects an array, a tuple of 3 elements of data. So imagine the client of this Socket.io server being developed by a completely separate organization. We would need the backend team to communicate with the frontend team and let them know about what events does the server support, what events does the server listen to. So I wouldn't want to live in a world where the answers to all these questions would be agreed verbally through some Zoom meeting. There should be a document which stands as the source of truth, and this is where AsyncAPI comes into play. Also bear in mind that we are not interested in Socket.io concepts that are specific to backend, to the Socket.io server. We are only interested in in concepts that are included within the Socket.io protocol specification. So rooms and broadcasting events is a server-specific concept that is not reflected anyhow in the protocol itself. Let's now move to the core of the talk, which is about modeling the Socket protocol, the Socket.io protocol using AsyncAPI. So the way I approach this problem is by traversing the AsyncAPI object structure, trying to map each of the objects to a semantic of the Socket.io client API. So I started with the root document object, the AsyncAPI object, which has 4 fields that are of interest to us. AsyncAPI, which is the pinning of the spec version that is being used. We have channels, which are all the available channels and messages for the API. We have servers, which provides connection details for all the server instances of our application. And we have components, which is essentially a library of reusable elements that we can reference across our spec file. So going one layer deeper, we can see the channels object, which is a mapping of channel names to channel item object. The specification states that the channel is an addressable component where messages or events flow through. It enables an application to separate its concerns. To me, this sounds very much like a Socket.io namespace. So there we have our first relationship between AsyncAPI and Socket.io, which is a Socket.io namespace is essentially an AsyncAPI channel. Going another layer deeper, we have the channel item object, which is essentially the values within the channels mapping. The channel item object describes the definition of a Socket.io namespace. In Socket.io, a connection can be established in the namespace level. So the channel item object is the only place in the specification where we can define bindings. And bindings are essentially protocol-specific information for the server. In the case of Socket.io, the bindings describe the handshake context on the connection request. So in this case, we have a WebSocket binding defined for the default channel, for the main channel, where it specifies a schema for the query params. This means that whenever a client wants to connect to that main namespace, they need to provide this token property as part of the query param object, and this token property should be of type string. And this is how it actually happens on the following implementation snippet below, where the Socket.io client establishes a connection passing this query param. There are a few conventions with regards to bindings, which I mainly came up with. One is that we can include bindings under the main namespace, but also we can omit them under the custom ones. This makes the assumption that the custom namespaces will inherit the bindings of the main namespace. However, if a custom namespace includes bindings, then the client should always force a new connection upon connecting to it. By default, a Socket.io client will always use the same connection when connecting to multiple different namespaces. And finally, the WebSocket channel bindings is the only possible binding that can be included in Socket.io API. And one would argue that we could also use an HTTP binding as well, since Socket.io can also be implemented with HTTP long polling. However, this is not possible for a couple of reasons. First is that the AsyncAPI specification does not allow HTTP bindings on the channel item object level. And secondly, is that in Socket.io, the HTTP polling implementation is done in such a way to resemble the WebSocket implementation. So essentially, the HTTP polling is a pseudo WebSocket, and both of the implementation use the exact same handshake object. So it is safe to assume that the HTTP long polling bindings would look exactly similar as the WebSocket ones. However, in an ideal world, we would have the AsyncAPI specification supporting Socket.io as a separate protocol. So the bindings object could have an explicit Socket.io field where one could provide bindings. I have created a GitHub issue in the bindings repository of AsyncAPI to pitch this proposal. So moving another layer deeper, next to the bindings field in the channel item object, we have operations which document how and why messages are sent or received. We have the publish operation, which is implemented using a socket.emit call on the client side, and we have a subscribe operation, which is implemented using a socket.on call on the client side, where the client registers a callback for an event to subscribe to. So there we have an extra two relationships between AsyncAPI and Socket.io. So we see that under each operation, either publish or subscribe one, there is a message field which defines a message object. And this is actually defining a Socket.io event that can be published or that can be subscribed to under a given namespace. In this case, here on line 5, we have an event with hello being the event name and payload being the structure of data that can be emitted as part of the emitification from the client. So this tells the client that under the main namespace, they can emit the hello event name using an object that has a foo field, which is of type string. Similarly, for the subscribe operation, the message object is used in a similar manner. So the name of the message defines the event name, and the payload defines the JSON schema that the input of the event callback should adhere to. We have seen, however, in this current setup, we only see that only one message for publish and one message for subscribe can be listed under a single namespace. However, in practice, we have seen that a namespace can support multiple different subscribing or publishing messages. So the way you can achieve that with AsyncAPI is by using this one-off array structure under the message field of each operation. So we've also mentioned that Socket.io provides acknowledgement functionalities. Before diving deeper into how this is achieved in the Socket.io protocol, let's first get some basic understanding of the protocol itself. So the basic unit of information in the Socket.io protocol is a packet, and there are 7 distinct packet types, as you can see on the left-hand side. A Socket.io sender invokes the socket.emit call in order to send an event to the receiver, and the event is conveyed to the receiver using the event or binary event package. Then the receiver acts upon these events using the handler that is registered using the socket.on invocation. The handler may, after it executes, may return or not return an acknowledgement back to the sender. The acknowledgement is sent back to the server using the ACK or binary ACK packet types. Then the sender is going to pass the acknowledgement data into the acknowledgement callback that has been provided as an argument in the original socket.emit invocation. In order to express these acknowledgement semantics, we have to extend the AsyncAPI specification. And AsyncAPI provides a good framework of doing that. So what I propose here is extending the message object to include an XACK field. The value of this field should be a message ACK object that we're going to cover in a bit. Also, the components object may include the XMessageAcks field, where one could list multiple message ACK objects that can be used throughout the specification file. And this is how the message tag object would look like. There is going to be an object of a single field, which is to be called args. The type of this field would be a schema object, and this would be the schema of the arguments that are passed as input to the acknowledgement callback function. And this is how it would look in practice. So, for example, let's take this socket.emit invocation, which is documented as a publishing operation under the main namespace. So this invocation is described using this hello event, which has an event name which is hello, and then a payload which describes the schema of the arguments, and then exac defines the schema of the input that is to be passed in this acknowledgement callback method. And similarly, for the socket on invocation, for the subscribing messages, the xargs schema defines the acknowledgement type that the event callback should return after it executes. So let's move on to the final object, which is servers, which is a top-level object. And this, as we said, defines all the server instances of our application. Each server instance is required to have a URL field as well as a protocol field. From the URL field, we can not only extract the host of our Socket.io server, but we could also get the path to our Socket.io server, which the client can pass when they instantiate a connection to that server, as we see here with that extra path argument. The path defaults to Socket.io, but it can be customized accordingly. Also, there is a protocol field within the server definition, which could be either of WebSocket, secure WebSockets, HTTP, and HTTPS. It doesn't really matter if it is WebSocket or HTTP, but it only matters if there is a secure character as a suffix to that protocol. So the protocol essentially signals the inclusion or absence in TLS for the server. So we made it to the end of this long modeling exercises. Here is a summary. So we did manage to establish a lot of relationships between Socket.io and AsyncAPI. For example, we said that the Socket.io namespace can be modeled using an AsyncAPI channel. The I/O options, the input-output options that the Socket.io client provides upon connecting to a namespace are essentially the WebSocket channel bindings. A socket.emit invocation is a publish operation of a channel item object, while a socket.on invocation on the client side is a subscribe operation within the channel item object. A Socket.io event is essentially an AsyncAPI message, and an event name is the name field of the message object. The arguments, the event arguments, are described by the payload of the message object, which is a JSON schema, and the acknowledgements can be achieved using the exag specification extension that we proposed. And lastly, we have the custom path to our Socket.io server, which is signaled using the URL field of the server object, and we have the absence or inclusion of TLS, which is using the protocol field of that server object.
Let's now get a bit more practical and look into how we can create an AsyncAPI YAML file from scratch given an existing Socket.io API. For the purposes of this, I picked this minimal chat application, which is featured as an example in the Socket.io website. It is a very simple application where the user enters a nickname to join the chat, and the rest of the participants get notified whenever a user joins, or whenever a user types or stops typing a message, or whenever someone leaves the party. I also put here the full implementation of the Socket.io server in JavaScript. It is not a very complex implementation. It doesn't exceed 90 lines. We're not going to go through each of the lines here in detail, but I put the full snippet here for anyone in case they want to review it on their own time. So let's start putting together our AsyncAPI YAML, and let's start with the simple things first, like pinning the AsyncAPI version, the version of the specification that we want to use, as well as putting together some information with regards to our service, like the title, the version, and some brief description of what it does. Also, we're going to have a server section, which we're going to define the server instances of our application. As far as I'm aware, this is an application that is only sitting in a single environment, so we're going to have just this demo server object, which has a URL as well as a protocol field. For the URL, we picked the actual URL that is within the Socket.io website source code, which is this Heroku app, and it also seems that they are using the default /Socket.io path. In terms of protocol, secure WebSocket is being used. Again, note that it doesn't matter here if it's WebSockets or HTTP long polling. The only purpose of this protocol field is to signal the inclusion or the omission of TLS. So, if here on the left hand side we have a simplified version of the Socket.io server code that we presented above, and we can see here that the server listens for connections under two namespaces. On line 3 we have the connection handler for the default namespace, and on line 7 we have the connection handler for the admin namespace. So we can identify that we have two channels here, the /default channel and the /admin channel. If we expand the connection handler of the default channel of the main namespace, we can see that there are multiple socket.on invocations. These are essentially the events, the Socket.io events that the server listens for from the client. So we have a new message event that is accompanied with some data arguments on line 5. On line 12 we have another add user event which has a username argument, and we also have the typing and stop typing messages that have no arguments at all, so no event payload is expected as part of this event. So these are the events that the Socket.io client can publish to the server under this namespace. So essentially these compose all the message objects that we can put under the publish operation in our AsyncAPI schema for that namespace. Similarly, we can also enumerate all the socket.emit invocations we can see with our namespace implementation. So on line 6 we have an emission to the new message of a new message event, and line 13 we have an emission of the user joined event, and so on and so forth. So these events are the events that the client can subscribe to and listen from the server. So essentially these are message objects that populate the publish operation of the default namespace of the default channel of our spec. So if we put this together in our YAML, we see that we have our main namespace, which has a publish operation and a subscribe operation, and under each under the message field of each operation we have all the different messages that are supported, and we achieve, and we of course use this one-off array structure that conveniently allows us to group multiple messages under an operation of its namespace. Now let's expand the connection handler of the admin namespace. We can see here that the handshake context of the socket is being used. This means that upon connection, the handshake context of the request is being used to extract some information. In this case, a token is extracted from the query parameter object of the request, and some validation is applied on top of that token. This signals us that we should include some bindings as part of the channel definition. So in this case we have the WebSocket bindings for the admin namespace that put together a schema, a JSON schema for our query parameters object, and this schema has a token property which is of type string, and it is always required. So if the token query parameter validation fails, the socket disconnects, otherwise the socket emits an event to the client, which is a server metric. And if you see, actually, if you were paying attention, this server metric event is also listed under the subscribe operation of the admin channel. So let's now move into how we can populate our message definitions within a component section of our schema. And for that we can expand the add user event handler of the default namespace. This event handler is being invoked whenever a user joins the chat application. So you see here, if the user is already added, so you see here that the inputs of our event handler is a username string and an acknowledgement callback function. So if the user is already added, then a callback function is invoked with an error which says a user is already added. So there could be an acknowledgement of this event by the format of an object which has an error property of type string. So if the user is not added, then we increment the number of users, and then we emit an event to the rest of the clients that are connected to that namespace that a new user joined. And this event has this particular argument structure of a username and number of users. If we are on the happy path scenario, of course, of not having the user already added, then we acknowledge that the user was added and the error of that acknowledgement is of null type. So we can see here that we can populate two message definitions. One is the add user message, which, as you can see here on the second line, it is the message that the server listens for. So it's a message listed under a subscribe operation. So it has an add space user event name and a payload of type string, since the username is the only argument of that event. We also see that within that event handler, an acknowledgement can be returned, and this acknowledgement has this following structure. It is an object containing an error field, which could be either string or null. So we can add this exarg field that we proposed as part of a specification extension, and this args object can describe the properties of the acknowledgement. For example, the error property that would be either string or null. Similarly, we see that an event is being emitted to all other clients, that a user has joined our chat. So we have the user space joined as the name of our event, and then the payload describes this object, which is essentially having a username property and a num_users property, which is of type integer. So now I think we can put together everything into a single specification file. So we see here we start with traditionally with a version of a specification, then we have the info and servers object, and then we have all the channel definition, which is the main channel and the admin channel, and within each channel we have all the messages under the publish and the subscribe operations respectively. You see here that the message definitions are actually referenced from the component section of our specification, as you see here. So I've sourced the this full setup in a GitHub repository under my personal account. So you can go to the Dedoussis AsyncAPI Socket.io example, which is a repository that includes not only this AsyncAPI YAML file, but also the source code of the Socket.io server and some README to document and instruct someone how to spin up this application. Another benefit that we get for free by documenting our Socket.io APIs is the AsyncAPI Playground visualization, which is a tool that receives an AsyncAPI specification as an input and produces a beautiful visualization of our API as an output. So here we can see all our operations of our API, we can see all our different messages, we can see that some messages have also defined extension. In this case, the add user event has an acknowledgement which has this error type argument. Similarly, we can see all of the different components, all the different messages of our specification, so it's a very nice way of communicating our actual API contract with other teams.
So finally, I would like to talk about Asynction, which is a tool that I've been developing in parallel to this modeling exercise of Socket.io with AsyncAPI. Asynction is a Python Socket.io framework that is driven by the AsyncAPI specification. It empowers a specification-first approach when building Socket.io APIs in Python, and it actually guarantees that your API will work in accordance with its documentation. So what Asynction offers in particular? It automatically registers all event and error handlers that are referenced within the AsyncAPI specification. It provides out-of-the-box validation on every Socket.io interaction. This means every incoming or outgoing Socket.io event. And this validation is fueled by the JSON schemata within the message payloads, within the channel bindings, and even within the exarg arguments objects that we previously mentioned. It also generates HTML render documentation similar to the AsyncAPI Playground and exposes it through a separate HTTP endpoint. There is also mock server support when one could spin up a fully functional mock server just used by referencing a local AsyncAPI file without the need of any extra code. There is also a CLI interface, and there is also an authentication feature coming soon, which will be based on the security schemes of the specification. So Asynction was originally inspired by Connection, and hence the naming. Connection is a framework, a Python framework for REST APIs, and it is driven by the OpenAPI specification.
On the left-hand side of this slide, we have a very simple OpenAPI specification of a Hello World API, where it has a single greetings name resource. As you can see here in this resource, there is a path parameter called name, and within that resource, we have a single post function. This post endpoint is related to a Python callable using this operation ID field. So the Python callable is actually a post greetings function within the hello.py module. So on the right hand side, you can actually see the hello.py module, which includes the post greeting method, and this post greeting method takes a name as an input argument, and this is the name which is the path parameter that we see here in this API resource. Also, this post greeting method returns a string output, and if we pay attention to the responsive specification of our endpoint, we see that it retains a text plain content of type string. So on the right hand side, going back to the right hand side, we see that it's very simple to spin up a connection Flask application only by referencing a local OpenAPI YAML and then running it as you run any other Flask app. And at runtime, connection is going to route a request to the appropriate callable, of course after validating all the input arguments based on the JSON schemata and so on and so forth. So Asynction does the exact same thing, but instead of OpenAPI, we now have AsyncAPI, and instead of Flask, we now have Flask Socket.io. So if we see again the AsyncAPI spec that we put together for the minimal chat application and go to the component section of the spec, we can see that, for example, here in this new message Socket.io event, we have a next handler field, which is actually another extension of the specification for the purposes of Asynction. This xhandler field relates this new message event to a Python callable which sits under the app.py module, and it is this new message function. So here the Socket.io client will emit a new message event to the server, and the server will look at this xhandler field in order to call the correct function, the correct Python callable, to act upon this event. Of course, Asynction will validate the input parameters that this callable will take, such as the message payload, or it will also validate what this function returns if there is an acknowledgement argument payload that needs to be validated. So here, how it looks on the Python side. Again, it is very simple to spin up an Asynction Socket.io server. You only need to reference a local AsyncAPI YAML file and then run the Asynction app like you run any other Flask app. And at the bottom hand side, you can see an example of a simple event handler that can be referenced within the AsyncAPI YAML. So you can find a fully fledged example of how to use Asynction in the Asynction repo under the top level example directory. This example also uses the minimal chat application AsyncAPI YAML and re-implements it in Python using Asynction. It is also fully documented, so if you're interested about Asynction and how you can use it, I would suggest to have a look there. And finally, another killer feature of Asynction is the mock server, which is also combined with the CLI. So you can install the CLI, the Asynction CLI from Homebrew using brew install Asynction, and then with a single line command, you can just reference a local AsyncAPI YAML file and spin up a fully functional Socket.io mock server. This mock server will listen for all the events that are referenced within the AsyncAPI YAML files and return acknowledgements appropriately based on the XAC schemata. It will also periodically publish fake events that adhere to the message payloads for any clients that may be connected to that mock server. So we have reached the end of this talk. Thank you very much for attending it. I hope you enjoyed it, and I hope that this talk was not just purposed for Socket.io enthusiasts, and I hope it could maybe have motivated others to start modeling more protocols with AsyncAPI spec, or even model protocols that are used internally within your organizations. So once again, thanks a lot, and I hope you enjoyed this. And I think now it's a good time for me to answer any questions you may have.